I'm coming from University of Glasgow. The other lab that is, or James Watt Nanofabrication Center is the other state of art in UK that we can fabricate very small devices like in Southampton. So we are supposed to be competitors, but we are not.
We're good friends.
Sorry?
We're good friends.
Yes, we're very good friends. So maybe this microphone makes a microphone here. So what we're doing, I'm part of device modeling group, and we do simulations. So I'm not going to talk about experimental data at the moment. What I'm going to show you, I'm going to show you something that is related with molecular base, but saying this after looking sensors and RRAMs. Is this okay? RRAMs here. After this, we can do a lot of different stuff. So let me just jump and show you. This is the device modeling group. He has been there around 25 years. The big name of the group is called Professor Asen Asenov, and he has been developing all of these things in the last 25 years. What we are very well known is something which is called statistical variability, and I already saw a picture that you used, so this was our picture. I will show you in a second a bit more. And we have different expertise in different things, like Monte Carlo, quantum transport variability, and so on. What I'm here is basically my expertise is more or less in the molecular electronics and quantum transport and variability. So what you can see here is that we can move, and we can, of course, we can do a lot of engineering, a lot of material design, and a lot of things, but we can improve things that they work well, right? And we can make it better. So one idea to do this is improving. So if you take a flash cell and you have a floating gate here, to put a bit of spice of chemistry. So you can put chemistry and see, okay, if it works, maybe it works. If it works, if it's better. So why we did this? Because EPSRC gave us money, basically, more or less, in a nutshell. But no, the idea is that this project, it was a platform grant in the University of Glasgow, and there were 3 groups involved in this, maybe more, 4. So 1 chemistry group and 2 groups in engineering. And the chemistry group, they synthesized the molecule, and the engineering groups, our device modeling group did the simulations, and the other group made the device. Basically, this was the plan. And this is what we did. And this is published in a couple of papers that you can see here on the bottom during the talk of the presentation. And as I said, we wanted to see, can we change the floating gate, or can you put this chemistry to make it work better? And I'll just give you a bit of chemistry. I know that I'm probably not on the right place to give you chemistry, but just to tell why we think that this might work. So this molecule is called polyoxymetallate from Greek. Poly is a lot, I guess, and oxygen and metals. So oxygen and metals. This is oxygen, and this is the metal. In this case, is tungsten. However, it can be anything else. This is so-called D element. It can be any D element, and can be bigger, smaller, peanut shape, any other shape. So this is the beauty of the chemistry, because you can synthesize more or less what you want. And you have some atoms in the middle, which in this case are selenium, but they can be something different. And eventually, maybe you can use this as a qubit, because they have spin states, nuclear states and spin states, in principle. So you can do stuff like this. Why they're cool? Because they're small, 1 nanometer diameter. They have low switching polarized state. I will show you in a second what I mean. They call them electron sponges. So if you move now and think about batteries, what you need on the batteries, on the electrons, you need to pump as much as more as possible electrons in the same volume, right? It is what you want to do. With these molecules, I'll show you in a second what I mean by this. You can pump a lot of electrons in one molecule. And in principle, either you can make it like electron sponge, or you make a multi-bit. So it depends from the resisting state, or depends from the things. And in principle, because it's so-called inorganic molecule, there is no carbon, and supposed to survive the CMOS process. It's supposed to be easier than the organic, because the organic just burning around 80, maybe 90 C. So this is a bit more stable. So far, so good. Now, when I started this project, me coming from chemistry and going to engineering, it took probably a year to try to understand what we are talking about, and we have the same language. So if you go to engineering department, this is the current voltage characteristic. So current versus voltage. If you go in the chemistry, and this is the chemistry picture, it's called cyclovoltagram. Current versus voltage. And what you do, you have a beaker, which is basically the cup. And you put your molecule inside, and you have 2 electrodes. One is called standard, the other is called working. So this is the standard, iron, and this is called, the other is the working. And what you do, you change the voltage between the 2 electrodes. And this is what it is on this axis. So I change the voltage between the 2 electrodes in the cup. And what I can record is I can record the current. So this is the current. So if I start changing the voltage from 0 and going to negative, what I'm going to see are, so these are simulations based on so-called density functional theory. So density functional theory is solving Schrodinger equation, basically, in a bit more optimized and useful, friendly way. It's very popular in the chemistry. This is what you do. If you go and do pharmaceutical stuff, you may use this as well. Over there is molecular dynamic, but depends. So this simulation, what it tells is this called HOMO, which is highest occupied molecular orbital, and this is LUMO, lowest unoccupied molecular orbital. And this, in semiconductor terms, is valence band, and this is a conduction band. And this is the band gap. So this is how you can read it if you come from the physics background. So if I increase the number of electrons, the voltage, I start adding electrons, and this in chemistry terms is called reduction. So I'm adding 1 electrons per molecule. So I'm start pumping electrons inside, and I can do this until I reach 6 here for this specific molecule. Okay, cool. What is more cool also is that if I reverse the bias, so it doesn't do anything, but actually I can take out this electron. So this peaks corresponds for me taking out the electrons. So I put 6, and I take them out back. And what you can see also is that you have on this side something which is called oxidation in principle. So you can start either with putting electrons or start either with taking out electrons. Depends what you want to do in principle. So I spent a bit of more time for chemistry just to give you what I think is important for the molecule. But this has a potential. So taking this into account, what the molecule eventually might do when it's in the cup of water in the 2 electrodes and stuff like this, is this possible to work in CMOS? Is it possible to put it on a device and actually measure something? So what we want to say is this. So if we have charge here in the floating gate, if you increase the voltage, you end up with voltage threshold. Sorry, so if this is the normal device without any charge, so increase the voltage and you have this blue curve, which is called so-called the erase device. If I put charge here in this, what I'll do, I'll screen the charge. So the gate there is a charge, and the electric field here will have less influence over the channel, basically, and I need higher voltage threshold, right? So I'm sure that you know this, just to be sure that we're on the same footing. And what is important is this delta VT, because you need to have delta VT, and if you apply VRead, you either read erased or read the program cell. So good. So can we do this? So as I said, I'm going to talk about only the simulations. We can talk about the experimental later. So this is, we combine the so-called 2 words of the simulation. So first principle methods, which are in this case, DFT simulations, density functional theory, and we use ADF program, which is a commercial package from Amsterdam. And we wrote our simulation domain bridge, and we use our device simulator to calculate things. Why we want to do this? Because it's practically impossible to simulate a device with DFT. No way, you cannot do it. So we needed to do something else. So what we did is we took the charges from this molecule, this the crystallographic structure. We wrote this simulation domain bridge and our simulator, and we transferred them to our device. So here you can see the potential. There is a source, drain, this is the device, and there is a floating gate, 1 molecule, and SAT. This is a cut through the device in the plane of the whiteboard. And this spinner shape, which is good or characteristic for the molecule here, is preserved here as well. If you do the same cut in this direction, this is this device. So basically, this simulation showed me that whatever I think and I understand with my chemical way of thinking actually is properly transferred in my engineer way of thinking and engineer way of tools. So I put my engineering hat now and saying, OK, let's see what we can happen. So just to show if the device works, I took a device, it's a bulk device against the potential. These are 9 molecules in a perfect grid organized here. 9 because the volume of the molecule is around 1 angstrom, the dimension, nanometer, and this is 18 by 18 nanometers floating gate. We have papers that they vary from 1 to 21 Poisson distribution, but I'm not going to talk about this. So just to be easier to understand. So what you'll see here is the current versus voltage, and I just increase the voltage and I record the current. My computer doesn't like me. So what you see here is a very similar picture. Let's skip to this one. So if you increase the numbers of the electrons once, you get the red curve, and you change the potential. If you increase the number of electrons twice per molecule, you get the blue curve. And you have delta VT shift, which exactly you should see, right? So this simulation told me that actually my simulator works, right? So I understand that if I increase the number of the charges in the floating gate, I see what I expect to see. So there is a delta VT shift. Now, the other things that we've been talking around, and this is a very old slide, but I really like it because experimental is very easy to understand, is the variability of the devices. So you have source, drain, you have a channel, and you have a device which is 200 nanometers width. And you scale it down from 200 gate length to 10. And what you see with the variability is that I don't remember how many devices, but let's say 100 or 50, let's say some number, and the VT is really localized. If you scale the gate length, the VT is all over the place. The story is even worse and much more pronounced here, which the width of the device is 20 nanometers right here. And you start with very high variability, and this is all over the place. So this is not good. I guess you know better than me why it's not good, so I'm not going to drill on this. So basically, this variability is big, and we don't want to have it. Or if we want, well, we cannot escape because it's the same like with the RAMs. Basically, you need to live with this, and you need to be smart, and you need to know how to solve the problem. So this is the device-to-device variability. Basically, when you squeeze the device, each device becomes atomistically different. And what we need to do, we need to evaluate this in scalability, variability, and reliability if you want to work with memory. But we will talk about variability in the moment. So we saw some pictures about the variability. What you can see here is that I took 1,000 atomistically different devices. What you can see here is the potential. Each dot here in the potential is the random dopant. So they have two sources of variability. One is random dopants in the source and the drain in the channel. And the other is random distribution of the 9. So fixed 9 molecules in the 14 gate. So I don't change this. And what you can see is that this device here is this device, basically this picture. And the dashed line here is the Poisson distribution. And of course, using statistics, we can see that you can take the average value, and you can say you have sigma as well, and we can establish something. If you take these 1,000 devices, what I wanted to see is that I wanted to see data VT shift, right? So is all of these 1,000 devices behave following more or less the Gaussian distribution, just in the brackets. Here it doesn't follow, which means that you cannot listen to analytical equations to describe these 1,000 devices if you want to be precise. If you go to, this is 2 sigma. If you go to 6 sigma, which is billion devices or something more, this will be on more debate. So basically, you need to simulate the devices if you want to be precise. Maybe analytical is not going to work. So this just was in the brackets. And if you increase more the charge, and the 14 gate, what you will get even higher voltage shift to the higher voltage threshold. The beauty of this is when you do simulations, most of the people that do this, you can disentangle. You can see what's going on, which in experiment is not very easy all the time. So if you go deep into details, I'm not going to show you the numbers, but you can see that the random dopant fluctuation have impact on the sigma. So how big are the best bell curves? What is the width? If you go a bit further, you will see that the average value is determined by the number of the charge of the 14 gate, which is not surprising. This is how it works. And now if you go a bit further, it's something that you don't like. These curves sort of overlap. So this is not a good news, because if I want to read the green curve with the highest probability, right, I still have a probability with voltage threshold to read blue and black and green. So I still have the probability, which is non-zero, to read any other bits or whatever signal it comes from there. So what you want to see something like this. Can we do this? Even if they're distributed because they're atomistically different, they're different devices, I know they are different, can they localized somehow in this way? Well, I really like this slide because you don't need to invent new material or make it new stuff. You can just change the device architecture. So if you move from bulk to fully depleted silicon insulator, basically you have oxide and you don't have a lot of doping here, what you're going to see is this. So this is what was in the previous slide. This is what is now, with just changing the device architecture. And this is cool because it's engineering, right? And so, and you go and do talks for material guys, and they, okay, so the changing the device actually matters. Indeed, the device architecture indeed matters. If you zoom in a bit at this, what you'll see is that the curves are much better separated. First, they're much more narrower, and the bell shape is much more compact. So sigma is almost 0.1. Also, they're move to lower voltages, which in principle, let's say, speculate, it can be for lower power applications. It's better in principle. And the other thing, if you do further, and if you just check the textbook, how delta VT depends from different parameters, it depends from the number of the charge of the 14 gate, the thickness of the controlling oxide, I'll show you in a second, and the number of the dielectric constant, so the dielectric constant. So we cannot touch this, we cannot touch this, but what we can touch this, we can touch this, the thickness of the controlling oxide. And what I can do, basically I can bring my molecules closer to the channel to make it thicker, the oxide, and I'm supposed to have a better delta VT split. So indeed what I did, I started with 3.5 nanometers above the channel, the molecules. If I bring them closer, you have moved from 0.78 to 1.18 and from 1.16 to 2.38. So the bell curves even much more separated. And if you don't have 1,000 devices, you have 6 billion devices or whatever you want to produce. They're not going to overlap. So I managed to be on time, good. And this is my last slide. And I hope I showed that we managed to combine different flavors of simulation from different worlds. I hope that I showed you that the variability matters and the sigma depends from the distribution of the dopants, and the molecules variability also matters, and this determines the average value. And changing the device architecture or just engineering the things, not changing the material and going something else, actually can solve our problems when we have them at some point. So this is me. Thank you very much, and I'm open for any discussions and any collaboration with anyone. So thank you very much.